What if I told you a computer just performed a calculation that would take every supercomputer on Earth, combined, longer than the universe has existed to complete? It's not science fiction. It happened in March of 2025 in China, and almost nobody outside the world of physics noticed. This is the story of Zuchongzhi 3.0, and why it just changed everything we thought we knew about the limits of computing. For most of human history, computing power has followed a simple rule. Faster meant smaller. Smaller meant more transistors packed onto a chip. More transistors meant more calculations per second. That rule gave us the entire modern world. It gave us smartphones that fit in a pocket, but outperformed the computers that sent astronauts to the moon. It gave us artificial intelligence systems that can write, paint, and reason. But that rule is starting to break down. Transistors are now so small that engineers are working at the scale of individual atoms. You cannot make something smaller than an atom and expect it to behave the way a normal switch behaves. At that scale, the strange and unpredictable rules of quantum mechanics take over, and the old playbook stops working. For decades, this was treated as a wall, a hard limit on how far classical computing could go. But a small group of scientists around the world looked at that wall and asked a different question. What if the strange behavior of atoms wasn't the end of computing, but the beginning of something entirely new? What if you could stop fighting the weirdness of quantum physics and instead harness it? That idea became quantum computing. And for a long time, it lived almost entirely in theory. Physicists wrote papers, mathematicians built models, but nobody could actually build a machine that used quantum weirdness to outperform a normal computer. Then, in 2019, that changed. Google announced that its quantum processor, named Sycamore, had achieved something researchers called quantum supremacy. Sycamore completed a specific calculation in about 200 seconds. Google claimed the very same calculation would take the most powerful supercomputer on the planet roughly 10,000 years to finish. The announcement made headlines around the world. It felt like the moment science fiction became science fact. A machine had done in minutes what classical computing would need 10 millennia to accomplish. Of course, it wasn't quite that simple. Within months, competitors pushed back. IBM argued that with the right optimizations, a classical supercomputer could actually complete Sycamore's task in a matter of days, not 10,000 years. That's still a staggering advantage for the quantum machine, but it showed just how contested and fragile these claims can be. The comparison between quantum and classical computing isn't a fixed number. It's a moving target, one that shifts every time classical algorithms get smarter and every time quantum hardware gets more powerful. This back and forth between improving quantum chips and improving classical countermeasures has defined the entire field ever since. It's a race with no finish line, only checkpoints. And while Google was making global headlines with Sycamore, another team on the other side of the world was quietly building something of its own. In Hefei, in Anhui Province, China, researchers at the University of Science and Technology of China had been working for years on a quantum processor of their own named Zuchongzhi. The name honors Zuchongzhi, a Chinese mathematician and astronomer from the 5th century, famous for calculating the value of pi to an extraordinary degree of precision for his era. It's a name meant to carry historical weight, linking ancient scientific achievement to a new frontier. The first meaningful milestone came in 2021 with a machine called Zuchongzhi 2.1. It had 66 qubits, and it achieved something significant. It became one of the first systems to demonstrate quantum computational advantage using a completely different technical approach than Google's Sycamore. Sycamore and Zuchongzhi both use superconducting qubits, but they're engineered differently, calibrated differently, and controlled differently. Zuchongzhi 2.1 proved China could compete at the absolute frontier of this technology, not just replicate what had already been done elsewhere. It was proof of independent capability, and in the years that followed, the team kept pushing. That brings us to March of 2025 and the unveiling of Zuchongzhi 3.0. This wasn't a small step forward. It was a leap. The new processor packs 105 qubits and 182 couplers onto a single chip. To put that in perspective, Google's original Sycamore chip that made headlines in 2019 had 53 qubits. Zuchongzhi 3.0 nearly doubles that number, and it does so while dramatically improving the quality of every single qubit on the chip. Now, if you're not deeply familiar with quantum computing, the term qubit probably needs a quick explanation because it's the entire foundation of why this matters. In a normal computer, information is stored in bits. Each bit is either a 0 or a 1. That's it. Every photo you've ever taken, every video you've ever streamed, every word processed by your phone, all of it eventually breaks down into strings of zeros and ones. A quantum bit, or qubit, works differently. Because of a property called superposition, a qubit can exist as a 0, a 1, or some combination of both at the same time. It's not that we simply don't know which state it's in. It genuinely exists in multiple states simultaneously until it's measured. Now imagine you have not just one qubit behaving this way, but dozens of them, all linked together through a phenomenon called entanglement, where the state of one qubit becomes tied to the state of another, no matter how they're arranged on the chip. When you connect many qubits like this, the number of possible states the system can represent doesn't grow in a simple, linear way. It grows exponentially. Adding just one more qubit to a system doesn't add a little more computing power. It can double the total number of states the system is capable of representing. That's why the jump from 53 qubits to 105 qubits isn't twice as powerful. In the right conditions, it's power on a completely different scale, because the computational space grows exponentially with every added qubit. This exponential growth is exactly why Zuchongzhi 3.0's benchmark results are so extreme. The team ran what's called a random circuit sampling task, using 83 of its qubits across 32 layers of operations. Random circuit sampling is a benchmark specifically designed to showcase what quantum computers do well and what classical computers do poorly. It involves running a sequence of random quantum operations and then sampling the probability distribution of the output. For a quantum computer, this is a natural, almost effortless process, because it's simply doing what quantum systems do. For a classical computer, simulating that same probability distribution requires tracking an enormous, exponentially expanding set of possible outcomes. It's the computational equivalent of asking someone to memorize every possible shuffle of a deck of cards, rather than just shuffling the cards themselves. According to the research team, this specific test was completed by Zuchongzhi 3.0 in a matter of seconds. Simulating that exact same task on Frontier, currently one of the most powerful supercomputers on Earth, would take an estimated 6.4 billion years. Let that sink in for a moment. 6.4 billion years is older than the Earth itself, which formed around 4.5 billion years ago. It's not a stretch to say that a task requiring more time than the planet has existed was completed by a chip smaller than a dinner plate in seconds. That comparison alone would be a stunning headline. But the story doesn't stop there. When researchers directly compared Zuchongzhi 3.0's results to Google's most recent quantum computing benchmarks, the ones published in Nature back in October of 2024, they found their processor outperformed Google's by 6 orders of magnitude. In plain numbers, that's roughly 1 million times faster on this specific benchmark. That's where the now widely repeated headline comes from. China's Zuchongzhi 3.0 running 1 million times faster than Google's most advanced published results. It's an extraordinary claim, and it comes from a peer-reviewed paper published in the journal Physical Review Letters, one of the most respected publications in physics. Reviewers reportedly described it as setting a new benchmark for superconducting quantum processors and called it a significant leap forward from the previous generation of the machine. But raw speed on one narrow benchmark isn't the only thing that matters here. What makes Zuchongzhi 3.0 genuinely impressive to physicists isn't just the headline number. It's the quality of the qubits themselves. In quantum computing, there's a concept called fidelity, which essentially measures how accurately a qubit performs its intended operation without introducing errors. Qubits are incredibly fragile. They're disturbed by heat, by electromagnetic interference, even by cosmic rays passing through the chip. Every one of those disturbances can flip a qubit's state or corrupt its data, a phenomenon researchers call decoherence. The entire history of quantum computing engineering has been a fight against this fragility. Zuchongzhi 3.0 achieved a single qubit gate fidelity of 99.90% and a 2-qubit gate fidelity of 99.62%, along with a readout fidelity above 99%. For comparison, Google's Willow chip, unveiled just months earlier in December of 2024, achieved slightly higher fidelity numbers, around 99.97% and 99.86% respectively. So, in terms of raw error rates, Google's Willow chip is still marginally more precise, qubit for qubit. But Zuchongzhi 3.0 closes that gap dramatically while offering nearly double the number of qubits, and that combination of scale and precision is what allows it to post such staggering results on benchmark tasks. How did the Chinese research team manage to close that gap so quickly? Part of the answer lies in materials science. Zuchongzhi 3.0 uses transmon qubits built from tantalum and aluminum, materials chosen specifically because they reduce sensitivity to environmental noise. The qubits are connected using a technique called flip chip bonding with indium bumps, a manufacturing process that improves the physical and electrical connections between components while minimizing contamination during fabrication. These might sound like small engineering details, but in quantum computing, small details are everything. A microscopic imperfection in a superconducting circuit can be the difference between a stable qubit and one that collapses into noise within microseconds. Speaking of microseconds, that leads to another critical number, coherence time. This measures how long a qubit can maintain its delicate quantum state before decoherence destroys the information it's holding. Zuchongzhi 3.0 achieved a coherence time of 72 microseconds. That might sound impossibly short, and in a sense, it is. But in the world of quantum computing, that's a meaningful improvement, giving the processor more time to complete complex calculations before errors creep in. Every microsecond of added coherence time effectively expands the ceiling of what the machine can compute before its quantum states become unreliable. Now, it's worth pausing here to address something important, because headlines about being 1,000,000 times faster than Google can create a misleading impression. Zuchongzhi 3.0 is not a general-purpose computer that outperforms every classical machine at every task by a factor of 1,000,000. It's not going to run your spreadsheets 1,000,000 times faster or load a website 1,000,000 times quicker. The comparison applies specifically to random circuit sampling, a benchmark deliberately designed to highlight the advantages of quantum systems. Researchers themselves have acknowledged that this benchmark, while scientifically meaningful, doesn't yet translate into solving practical, real-world problems. It's closer to a specialized athletic event than an all-around fitness test. A world record sprinter is extraordinarily fast over 100 meters, but that doesn't necessarily mean they'd win a marathon, or a swimming competition, or a chess match. Zuchongzhi 3.0 is winning a very specific, very demanding race, one engineered to expose the weaknesses of classical computers and highlight the strengths of quantum ones. That distinction matters because history has already shown how quickly these gaps can shrink. When Google first claimed quantum supremacy with Sycamore back in 2019, the initial 10,000-year comparison to classical supercomputers was eventually challenged. Researchers at IBM argued that with better classical algorithms and more efficient use of existing supercomputing resources, the same task could be completed in a matter of days rather than millennia. That doesn't erase Sycamore's achievement. Days versus 200 seconds is still an enormous advantage. But it's a powerful reminder that these numbers are not permanent scientific facts carved in stone. They're snapshots in an ongoing competition. Every time quantum hardware makes a leap forward, classical computing researchers respond by refining their algorithms and finding smarter ways to simulate quantum behavior. It's entirely possible that within a year or two, someone will develop a classical algorithm that narrows Zuchongzhi 3.0's 6.4 billion year comparison down to something far smaller. That wouldn't diminish the achievement of building the chip. It would simply reflect how competitive and fast-moving this entire field has become. Still, even with that caveat, the trajectory here is impossible to ignore. In 2019, Google needed 53 qubits to claim quantum supremacy. In 2021, China matched and diversified that achievement with 66 qubits on Zuchongzhi 2. In December of 2024, Google unveiled Willow, pushing further into questions of error correction and scalability. And by March of 2025, China had already responded with a 105 qubit machine posting benchmark results 1,000,000 times beyond Google's own published numbers. This is not a story of one country pulling ahead and staying there. It's a story of two of the most technologically advanced nations on the planet locked in a rapid, iterative competition, where the lead can shift within months and every new announcement raises the bar for what comes next. And this rivalry isn't happening in isolation. It's part of a much bigger geopolitical and economic story. Quantum computing is widely considered one of the defining technologies of the 21st century, alongside artificial intelligence and advanced semiconductor manufacturing. Governments around the world have poured billions of dollars into quantum research, not just for scientific prestige, but because the implications of this technology touch nearly every strategic industry imaginable. Quantum computers, if they mature into stable, large-scale, error-corrected machines, could revolutionize drug discovery by simulating molecular interactions with a level of precision classical computers simply cannot achieve. They could transform materials science, enabling the discovery of new superconductors, better batteries, and more efficient solar cells. They could reshape financial modeling, allowing for far more sophisticated risk analysis and trading strategies. They could dramatically improve weather forecasting and climate modeling by simulating enormously complex atmospheric systems. And, perhaps most consequentially, they pose a direct threat to modern cybersecurity, because a sufficiently powerful quantum computer could theoretically break the encryption methods that currently protect everything from banking systems to national security communications. That last point is why governments treat quantum computing not just as a scientific curiosity, but as a matter of national security. Whoever achieves reliable, large-scale quantum computing first doesn't just gain a research advantage. They potentially gain the ability to break encryption that the rest of the world still depends on. This is part of why the achievements coming out of both American and Chinese labs are followed so closely, and why breakthroughs like Zuchongzhi 3 Zero generate headlines that go well beyond the physics community. It's also why so much current research is now focused on something called post-quantum cryptography, an entirely new generation of encryption methods designed to remain secure even against future quantum attacks. But before anyone starts panicking about encrypted data being cracked open tomorrow, it's important to understand exactly how far current quantum computers still are from that kind of practical threat. Breaking modern encryption standards using an algorithm known as Shor's algorithm would require not just more qubits, but qubits that are stable, error-corrected, and capable of running long, complex calculations without failing partway through. Zuchongzhi 3.0, impressive as it is still what researchers call a noisy intermediate-scale quantum device. In simpler terms, it's powerful, but it's still fragile, still prone to errors, and still far from the kind of fault-tolerant, large-scale quantum computer that could actually threaten encryption in the real world. The gap between winning a specialized benchmark like random circuit sampling and running a stable, error-free algorithm capable of breaking real-world encryption is still enormous. Scientists generally agree we're likely years, possibly a decade or more, away from that kind of practical threat becoming real. That brings us to one of the most important developments in this entire story, one that arguably matters even more than the headline-grabbing speed record. In December of 2025, the same research team behind Zuchongzhi 3.0, again led by Pan Jianwei, announced an upgraded version of the processor, called Zuchongzhi 3.2. And this announcement wasn't about raw speed at all, it was about stability. The team reported that their machine had reached what's known as the fault-tolerant threshold. This is one of the most significant milestones in the entire field of quantum computing, and it deserves real explanation because it represents a fundamentally different kind of achievement than simply running a fast benchmark. Here's the problem fault tolerance is meant to solve. Quantum error correction is famously difficult because the very process of trying to correct errors in a quantum system can accidentally introduce new errors. Imagine trying to fix a leaking pipe, but every tool you use to patch one leak accidentally creates a small new leak somewhere else. For years, that's essentially been the challenge facing quantum engineers. As you add more qubits to try to protect information through redundancy and more complex error correction procedures to detect and fix mistakes, you also introduce more opportunities for new errors to sneak in. Crossing the fault-tolerant threshold means reaching a point where error correction actually improves overall system stability, rather than working against it. Below that threshold, adding more error correction can make things worse. Above it, adding more error correction makes the system progressively more reliable. It's the tipping point between a technology that's fundamentally unstable and one that can, in principle, be scaled up indefinitely while becoming more reliable, not less. According to the South China Morning Post's reporting on this announcement, the team achieved this milestone using microwave-based control methods, which stands in contrast to the more hardware-intensive error suppression techniques that Google has relied on with its Willow chip. In their own public statement, the researchers suggested that their approach could offer a more efficient path toward building large-scale, fault-tolerant quantum computers than the method Google has been pursuing. If that claim holds up under further scrutiny and independent replication, it could represent a meaningfully different and potentially more scalable route toward the ultimate goal of the entire field, a genuinely fault-tolerant quantum computer capable of running long, complex, real-world algorithms without being overwhelmed by errors. This is worth sitting with for a moment because it reframes the entire narrative around Zuchongzhi 3.0 and its successors. The initial headline, 1 million times faster than Google, is eye-catching, and it's rooted in real, peer-reviewed science. But taken alone, it can make this feel like a story about a single dramatic speed record, a kind of scientific sprint. The deeper story, the one revealed by the follow-up work on Zuchongzhi 3.2, is about something slower, quieter, and ultimately more important. The long, difficult march toward genuinely stable, error-corrected quantum computers. Speed records grab attention. Fault tolerance builds the actual foundation for a future where quantum computers move from laboratory demonstrations to tools that can solve real-world problems in medicine, material science, logistics, and beyond. So where does this leave the broader competition between the United States and China in quantum computing? It's genuinely difficult to declare a single, clear winner, and that's not an evasive answer. It's an accurate reflection of how fast-moving and multidimensional this field really is. Google's Willow chip still holds a slight edge in raw qubit fidelity, meaning each individual qubit on Willow is marginally more accurate than each qubit on Zuchongzhi 3.0. Google has also placed enormous emphasis on demonstrating logical qubits, in which several physical qubits are combined and error-corrected to behave as one highly reliable computational unit, a different but equally important approach to the fault tolerance challenge. Meanwhile, China's Zuchongzhi line has demonstrated a clear and consistent pattern of rapid scaling, expanding from 53 qubits worth of complexity in the earliest comparisons to 105 qubits by 2025, while simultaneously closing the fidelity gap with Google's best hardware, and now claiming a fault-tolerant threshold breakthrough of its own using a distinctly different technical approach. What's happening here isn't really a single race with one finish line. It's closer to two parallel competing research programs, each pursuing fault-tolerant quantum computing through somewhat different engineering philosophies, each achieving major milestones within months of one another, and each pushing the entire field forward through that very competition. In a strange way, the intensity of the rivalry between the United States and China in this space may be accelerating overall global progress toward practical quantum computing faster than either country could achieve entirely on its own. Competition, even fierce, high-stakes, geopolitically charged competition, has a long history of driving scientific breakthroughs at a faster pace than isolated research ever could. It's also worth remembering that these two countries aren't the only players in this story. Companies like IBM, Microsoft, and Amazon are investing heavily in their own quantum computing platforms, often using entirely different underlying technologies, such as trapped ion systems or topological qubits, rather than the superconducting approach used by both Google and the Zuchongzhi team. Startups around the world are exploring alternative paths as well, from photonic quantum computing to neutral atom arrays. The race toward practical quantum computing is not a simple two-country contest. It's a global, multi-front effort with breakthroughs emerging from labs in the United States, China, Europe, and beyond, each contributing pieces to a much larger puzzle. So what should you actually take away from all of this? First, the headline is real, and it's backed by legitimate peer-reviewed science published in one of the most respected physics journals in the world, Zuchongzhi 3.0. Zero genuinely did outperform Google's most recent published quantum computing benchmark by roughly 1 million times on a specific, scientifically meaningful test called random circuit sampling. That's not hype. That's documented, verifiable research. Second, that number applies to a narrow, specialized benchmark, not to general computing performance, and history strongly suggests that gaps like this one tend to narrow over time as classical algorithms improve and as rival quantum systems catch up. Third, and perhaps most importantly, the true significance of this story isn't really about who currently holds the speed record. It's about the broader trajectory. Both the United States and China are making consistent, rapid progress toward the real goal of quantum computing, which isn't winning a single benchmark, but building large-scale, fault-tolerant machines capable of solving problems that no classical computer, no matter how powerful, could ever solve. And with the fault-tolerant threshold breakthrough announced in Zuchongzhi 3.0. 2. Just months after the original speed record, it's clear that goal is getting closer, one carefully engineered qubit at a time. We are living through the earliest chapters of a technological shift that future generations may look back on the way we now look back on the earliest days of classical computing, back when a single computer filled an entire room and could barely perform calculations that a modern smartphone handles instantly without a second thought. The machines making headlines today, with their exotic qubits, their near-absolute zero cooling systems, and their almost incomprehensible speed comparisons, are the room-sized computers of the quantum age. Clunky, fragile, astonishingly expensive, and still, in many ways, experimental. But they are also the direct ancestors of something far more powerful still to come, somewhere between the extraordinary speed of Zuchongzhi 3.0 and the quiet, patient stability breakthrough of Zuchongzhi 3.0. 2. We're watching the opening moves of a technology that could eventually reshape medicine, materials, cybersecurity, and computing itself in ways we're only just beginning to imagine. And that's really the story worth remembering, long after today's exact numbers get revised and surpassed by whatever comes next. Not a single machine or a single country, but a steady march toward a kind of computing power humanity has never actually possessed.